Our next speaker is Dr. Wenrui Hao, and he's an associate professor from the Department of Mathematics at Pennsylvania State University.
Okay, thank you for invitation. Today I will talk about computational modeling of Alzheimer's disease. And I will, based on this mathematical model, I will talk about some personalized optimal treatment. So this is my outline. So the first, I want to introduce a new mathematical model. It's based on Alzheimer's disease biomarker progression. And then we use some data from ADNI data set to validate this mathematical model. And not only validate, we also want to verify the model. So this here is the two terminology. One is called validation, which is using data to validate a calibrated model, find the parameter. Second one is verification. Then you can use data really confirm what equation you wrote is right. Okay, so after that, after validation and verification, I will talk about some optimal treatment. So this is based on mathematical model, is a so-called optimal control theory. So let me start very beginning. So probably this figure, you know, pretty much is from 1907. First, we have this name of the disease, and after in the several decades, we have different biomarkers and different benchmark. Then eventually, the start from 2000, we got a lot of data. Okay, so then this data is based on clinical biomarkers. The question is, can we use this data to validate a mathematical model? This will become really important. Once you write in a mathematical model, then you can use the data to make this model is real model, so really reflect what we have in the clinical understanding. Okay, so this is back to the 2016, we developed the first mathematical model here. So this is a very complex mathematical model. So we have two parts. One is intercellular, what happens in the cell, and another one is intercellular, what happens beyond the neuron. So it's most of case we want to integrate all our possible understanding into a system of partial differential equation or ordinary differential equation. So you through all the biological hypotheses into mathematical models. So this then you can integrate all the understanding or possible understanding to see if this hypothesis is really helpful to understand the AD progression. So we, based on this mathematical model, we can list a system of 20 or 30 equations, but the problem is we don't know the parameter. Okay, so we really don't know we don't have any understanding for each pathway. So even we can borrow some parameter from other diseases, for instance, cancer, cardiovascular disease, or pancreatitis. But this is still a theoretical model. Is we really cannot apply to a real AD. But the question is, why do we need a mathematical model? So this let me give you two examples. So this is pretty successful in cardiovascular disease. And on the one side, you can integrate all the understanding of this disease. This disease is based on aneurysm. So you can really build a complex network. Then you can write into a differential equation. Not only this, you can see how the different cells they will interact with each other. Then you can build a complex network. This is the one side you have really biological network. I call it pathophysiology driven. And the second one is actually you can not only based on the biological network, you can also include the physical property. For instance, you have multi-arterial wall, what's the property you have? You have brain, what's the porous elasticity you have? So you really have a biological part and the physical part, you integrate together. We want to have a so-called digital clinical trial. This is a digital twin, right? So then after you have this model, then you can integrate all the data over here. So then you can calibrate your model. Then you can really have the precision medicine platform. Okay, based on this platform, then you can do some treatment. This can really reflect what's this personalized treatment. So that's the whole idea of the general modeling. So let me apply this to Alzheimer's disease. And when we can't first we develop a complex network, but we realize we only have this available, several biomarker data available. So you have amyloid beta, tau protein, and the neuron inflammation, right? So you have different resources. You have CSF, plasma, imaging data. So the question is, how can we use this data? So you can think about a clinical biomarker-driven model. We only concentrate on these 3 biomarkers. Is that possible? We can build a mathematical model. So this model is based on cascade hypothesis. So this is first you start with the amyloid beta, right? So then once you have A beta, you will trigger tau protein. Once you have tau protein, you will stimulate the neuron inflammation or neuron degeneration. Eventually, you cause the cognitive decline. So this is a cascade model. So if you based on this cascade model, you have a lot of network over here, but mathematically speaking, it's quite simple, or biologically speaking, it's quite simple. You only have 4 biomarkers, right? A beta, tau, neuron inflammation, and cognitive impairment. Okay, so then I want to write into an equation. So this equation is called a system of ordinary differential equation. So you have different biomarkers over here. You have A beta, you have P tau, you have tauopathy, neuron inflammation, and the cognitive impairment. Okay, so the only thing you have is the A beta DT. So this is the biomarker. You want to model what's the rate, growth rate for each biomarker. Okay, if you look at the right-hand side, if the A beta you have, this is called the logistic growth model. So you have S shape, and the K is the carrying capacity. So if you start with very little, and eventually you go to the carrying capacity, you stay there. So you have S shape. So once you have A beta, then you can trigger tau. So this is the production rate for tau. So again, once you trigger the tau, then tau also follows the logistic growth. Okay, and similarly, once you have tau, you go to the neuron inflammation or neuron degeneration, then you have logistic growth, and eventually you finalize that cognitive impairment. So this is a model, and it's not only the very simple term is logistic growth, okay? But you have cascade model. You start with tau, you start with A beta, go to tau, go to N, then go to C. So this is quite simple. So you only have the cascade modeling hypothesis over here. Okay, so this is a very theoretical result. So we bring a bunch of parameters over here, and eventually we can see. So you start with A beta, right? So then once A beta is getting the detection threshold, then you can, next you will find the tau. Once you have tau, you can have the neuron degeneration. Then you have high risk area of the cognitive impairment. So this is the one way. So if you change the parameters, then you can have even A beta starts to first, but sometimes tau you can detect first. So this is you have tau first A beta. Okay, so you can. So this is the whole idea is we have a theoretical model. You take the parameter, you can have the different representation. You can have the different phenotype of AD, right? So this is the early onset, one is the late onset, tau first. Okay, so far I just write on the model. I didn't use any data. So next one is, can we use some data to calibrate a model? So this is really have the personalized model. The idea is the following. So if you have a patient, you have longitudinal data, for instance, one patient comes to the AD data set, you have baseline, you have 6 months, 12 months, 18 months. So the question is, can we use this longitudinal data to calibrate all the parameters in the model? Then we can use this model, it's kind of a personalized model to give a personalized prediction and also the diagnosis. Okay, so here, because we didn't include any of the spatial information, we only use the longitudinal data. So we use a different biomarker. use a CSF biomarker for A beta and P tau. Then we use a hippocampus volume for neuron inflammation. Okay, so the last one is ADAS13 to see what's the cognitive function. So you have 4 biomarkers. I have 4 type of data over here. I want to validate. Okay, so here's the one patient, for instance, if you see is one of the patient that you use RID to demonstrate for different patient, then you have different longitudinal data for A beta, tau, and neuron inflammation. Okay. So then I come to a mathematical question over here. So I just summarize everything is dx equals g of xp. Okay, p is my parameter, x is biomarkers. You can have the A beta, tau, n and c. So you have vector of biomarkers. Then I don't know the p, right? So if you give a p, I can simulate a model, find what's the trajectory for each biomarker. But how can we calibrate the model? So that means I want to use the data fitting into the model to find the parameter. So eventually, this is called L2 minimization. So you have model. So this model is x. You have t, you have p. So if you change the parameter p, you will change your model. Then you run the ODE model, you will get a different trajectory, right? So then you have data executor. So this data is discrete data. So for different TI, you have different executor. So again, x is a vector. So I want to quantify or minimize the distance between my model and the data. Okay. By minimizing the distance, I want to find what's the parameter. So this parameter is a high dimensional parameter space. It's normally it's a convex optimization. It's hard to compute, but the beauty of our model is a cascade modeling hypothesis. So you start with A beta, then you go to tau, go to n, go to c, right? So in this case, you can do the calibration equation by equation. So you can calibrate parameter for A beta by using A beta data only. Okay, so then once you find the p, then you go to tau, then you go to neuron degeneration, go to c. So this actually, so this is a high dimensional parameter, high dimensional optimization problem. We can reduce to a low dimensional optimization problem, even if it's still convex, non-convex, but it's much easier to solve it. Okay, so let me give you some results. I just ignore all the mathematical details here. So if you are interested in, you can refer to our paper. So this is 3 groups. We have CN, MCI, and AD. Okay, this is a different patient. So you have for red is A beta, blue is tau, yellow is N, and the red one, green one is the cognitive impairment. So okay, cognitive function. So you have different data. So this is a data point. Then we can calibrate each of the trajectory. We can find the personalized parameter for each patient. Okay. So after that, you can see. So you can, for different patients, you have really different trajectories. A little bit different. Sometimes it's a straight line. Sometimes it's you have this still can recover the S shape. Okay, so this is the logistic growth. So anyway, so this is once you have data, you can put into the model to find all the parameters. And the second one, we want to do the prediction. So this is a prediction. You have predictor A beta, tau, neuron degeneration, and the cognitive impairment. So this is the predictor value. So this is the real value. So then we do a linear regression to find what's the x and the y. So coefficient, you can see the slope is very close to 0, and this value is quite small. It's 0.01, 0.05. Okay. So then we have the different patient. Okay, so for the different related MSE, so you have the percentage. So in other words, if the prediction accuracy error is smaller than 10%, its prediction accuracy is above 90%. So most of cases, they are around 90%. So this is the number of patients we can have. But you still have some outliers. So you have 40 or 50 error. So in this case, it's based on what's the number of, we don't have enough data points. So we need at least 3 or more than 3 longitudinal data, then you can fit all the parameters, because then that's an ODE model, you want to see what's the trajectory of each patient. Okay. So this is the first part. We write down the model, then you can give a personalized prediction. But the question is, okay, if you write down the model, how can I trust your model? Why you have logistic growth model, right? So why is the quadratic term? So could we have the more complex model, right? So that means, okay, if we only have data, can you through the data to learn what's the mathematical model you have? So I know the X is the biomarker data. I know you have form dx dt equals gx, but the right-hand side, I don't know, okay? So how can you learn the right-hand side? So this is the right-hand side is mathematically speaking, as long as you have is so-called approximation theory, then you can write on the right-hand side by different bases. So this you can choose the different basis of x, you can have the polynomial, or you can have neural network, or you can have the sine or cosine. As long as they have approximation theory, you can write into the right-hand side. Okay, do the expansion. We call it the expansion. Okay, so here I use a polynomial because I want to use a polynomial basis to compare what we learned through the data and what we have in the cascade model before. Okay. So over here, so let's write down the mathematical ODE model. I rewrite, this is the one. Then the only thing I know the basis, the only thing I don't know is the coefficient. Okay, so then I do the integration for this ODE model. So eventually I can write into a linear system in terms of WL is a coefficient. Okay. So how do you do this? I need throw all the data into the model. For different patients, you have different disease progression. So we need to introduce a disease progression score for different patients. So for instance, some people start AD at 60, some people start at 70, and some people get AD in 5 years, some people get in 10 years. How do you do this, right? So we just introduce a disease progression score. So for each patient, so you have T is a real lifespan. So you have alpha I is when you have the disease. Okay, if the SI equals 0, this is really you start the disease. Okay, so the beta I actually is tell you how fast you get the disease. So this is really slope of the disease progression. Okay, but alpha I, beta I, we don't know either, right? So we just write everything into a very complicated network. So you have one side, I want to learn what's the WK is the coefficient in front of each basis. So right hand side of the ODE. And we also want to solve the alpha and the beta. So in this case, I break in 2 steps. The first one, if the alpha and the beta is given. So for instance, you can have alpha equals 0, beta equals 1. You fix the alpha and the beta, you solve WI. So you learn the model, right? So over here, so you have XIJK. So this is X tilde is data. So you have K is biomarker because X tilde is a biomarker vector. So you have K equals 1 is A beta, K equals 2 is tau, K equals 3 is N4 is the cognitive impairment. So then you have S patient. So we also give the number for different patients. So you have S patient and J visit. So in this case, for each patient, you have multiple biomarkers. You also have longitudinal data. Okay. So the first step, if alpha beta is fixed, can you learn WK, right? So the second one is okay. If the WK is fixed, can you update alpha and beta? So that's the 2 steps. So you can have, then eventually you do the iteration until it converges. So this is typically we are using in mathematics, it's called a splitting method. So you can fix one because impossible you update everything in one time. So how about we fix some parameter, update another one, then once we get this group of parameter, then we update on the other group of parameter. Okay, so after that, so let me talk about this framework, what we have. So we have the general ODE model. We don't know what's the right-hand side, but we can do the representation by basis. Then we put all the clinical data over here. Okay, once you have clinical data, then you have different alpha and beta I. Then we can learn our population model. Okay, once you have population model, we do the sensitivity analysis on the parameter space. So then we know which parameter is more sensitive. Then we treat the sensitive parameter as a personalized parameter. Then we fit the personalized data. So eventually we have personalized model. Okay, so you have all the data, all the patient you threw in to learn population model. Then once your population model, you have personalized model. Okay, so this is the general model we learn. So from here you can see once you learn the model, you can really recover the quadratic term. So in another word, you have logistic growth model. Then you also have cascade model. You start with A beta, you trigger tau, then you have tau, you have n, then you have cognitive term. So this is echo what we had is a cascade model hypothesis. Okay, so this is once you have population model, we can use this population model to do the classification. So you have different group, you have CN, you have AD, you have MCI. Then you, by using our model, use this DPS disease progression score, you can really separate. You have CN, you have AD, in between is LMCI. Okay? So, but it's more important we can do the personalized treatment. So you identify personalized parameter. For instance, if you have 5 longitudinal data, you use the first 4 to learn the model, okay, learn the parameters. Then you have trajectory, then you can compare with the last one. So we can do the prediction accuracy by using this personalized model. So this is our model. So if you use a different group, you have disease group, you have CN group. So you can have almost 90% of prediction accuracy. So this is a cognitive impairment is lower, is 80%, but compared to the traditional statistical method, you're already 10% prediction accuracy improved. Okay. So here is nothing fancy math, is only ordinary differential equation. So then actually you can improve the prediction accuracy. So then how you use this model? So probably even you give a prediction for AD or MCI people, but it's not very useful. It's, you just tell them, okay, after 1 year or 2 years, you will have AD, right? So how can we use this our model to do some clinical trials? So this is we want to apply to the anti-beta and aducanumab. So you know that it's controversial, but the problem is in the clinical trial, they only do certain treatment regimen, right? So can we have the personalized optimal treatment for each patient by using mathematical model? So this is our goal. We want to build our personalized treatment over here. So this is we use some clinical trial phase 3 study, so we can get what's the trajectory regimen over here and what's the clearance of the anti-beta. So okay, so this is this is the public data set, is the data you can get from the website. And then we go back to the model. Let me write on the model is a more understandable way. So actually you have a cascade model. So you start with A beta, then you go to tau, go to neuron degeneration, go to cognitive impairment. Okay, so this is all equation I have. And over here, I also don't know what's the initial condition. So I also put all the initial condition as a parameter we want to learn through the data. So the first, we still use the ADNI data set and let's see if we can have the personalized model based on the ADNI data set. So you have AD, CN, and MCI. We just threw all the longitudinal data to learn what's the trajectory. Whole point that I want to learn the personalized parameter. Okay, so once I learn the personalized parameter, then I can give the anti-A beta treatment. So that means you start with A beta, I give a control function U of t. This stands for dosing function with respect to t. So this is how much you give anti-A beta. Okay, so then what's the objective function? You want to minimize the cognitive impairment, and also you want to minimize the side effect. So in this case, we can write into our optimal control theory to apply. So eventually, if we compare what we have, so the short-term treatment, 70 weeks. So this is consistent with the clinical trial. So you can see this is personalized treatment. You have low dose and high dose, and eventually you want to start the dosing is very small because you want to minimize the side effect, and eventually you take the maximum dose. Okay, so this is, but after that, for the cognitive impairment is the minimum. You don't see much difference. This is the control is blue, the black is no much difference. Then I plot the cognitive change percentage. So you can see over 78 weeks. So this is almost 10 to the minus 5%. So this is very minimal. So if you go to the 10 years, so normally you cannot do 10 years, but you can use a mathematical model. You can still have the same regimen over here, but the percentage change a lot, 0.04. Okay, so this is only for one patient. So how about you apply to the whole data set? So I just apply to the two groups. One is MCI, one is AD. So you have short term and the long term. You one group you start at the age 60, one group start at the age 70. So you can see if you start earlier, so you can have better efficacy. So this you can improve the 3.5% of cognitive impairment, and also the high dose is better. Okay. So then I want to see, okay, so how about the different racial group? Okay. So I also see what's the black people and the white people. So here we didn't really distinguish black people and the white people in our model. We want to use this parameter estimation. We want to use all the parameters to capture all the difference between the black people and the white people. Okay, so that's from here you can see the black people is actually much more efficacy. It's very high. It's twice of the white people. Okay, but it could be this data is not enough because the aging data we at least use the 3 longitudinal data set. So then eventually you don't have much people in this group. So anyway, so let me conclude my talk here. So I developed a mathematical model for AD clinical biomarkers. Then you can use this model to do some personalized prediction and also treatment, optimal treatment. So you can minimize the side effect and also minimize the cognitive impairment. So what we are doing next is we want to introduce all the imaging data. So then you can extend the ODE model to a PDE model. Then you have a more reliable mathematical model here. Okay. So so this is my collaborator. Is an amazing team, and Jeff and Morali here, and also we have a bunch of students and collaborators from Duke and the UK. And this research is funded by NSF through the MathBio program, and also NIH through the mirror work. So I'm happy to take on the question if you have.
Okay. So your model is pure deterministic, right?
Right, deterministic.
So you don't do you have plan to introduce stochastic component?
What component?
Look, I'm asking because what is most precisely known is the risk of Alzheimer's disease versus age.
Right.
So far you have a pure deterministic model, you can't predict it.
Right.
right?
Right.
And so it would be nice if you can distinguish between different individuals by distribution, for example.
Yeah.
Maybe different dynamics, and in this way you will be able to predict the age pattern.
That's very,
Very well known experimentally measure.
Yeah, exactly. This is a very good question. Actually, during lunch, we talk about you not only give a prediction, probably you give a confidence intervals. What's your prediction? Maybe that's so this is we are.
So, and also we have a question from audience. So, how do you solve your equation? Do you use MATLAB, Simulink, or how do you implement this approach?
Oh, so this is very traditional. You can use the MATLAB. There is a built-in function. It's called the rank-kata method. You can simulate a model. That is not necessary in MATLAB. Right now we are using Python. We still have the built-in function. Yeah. So many packages for it.
The math is way over my head, so I have a pretty basic probably question for you.
Sure.
But the cascade, the amyloid cascade computational model that you one time, is this model specifically built based on these pathologies, or can it be replaced with different?
Oh, you can replace.
So it's really anything that you think follows this computation.
So for instance, that's the beauty of the computational model. So if you want to have some hypothesis, right, you just build a hypothesis in your model to find it. Yeah, you could have any network you want.
Okay,
right?
thanks.
Okay, I know we're running tight on time. You are using quadratic equations, and therefore there are three outcomes from these equations. One is periodical, the second is deterioration of health, the third one is the deterioration and of restoring and health. Did you see any individual that fall to the last example?
That's the example of what?
With the deterioration, it's like half of Alzheimer disease, and the healthy patient.
Oh, okay. So how about I talk to you later? So I make sure I understand your question.
Thank you.